Welcome, comrades perennials, to another episode of the audio podcast, Synthetic. Artificial intelligence will not replace you, but someone using artificial intelligence definitely will. Carbon is, it's arguably the most fascinating shapeshifter out there in the known universe.
Oh, absolutely. I mean, it's everywhere.
Right. Like, you are probably highly familiar with the everyday forms. You've got graphite in your pencils. You've got ordinary diamonds in jewelry.
Yeah, and you've probably read about the more exotic stuff, too.
Yeah, like those one-dimensional nanotubes or two-dimensional graphene.
Right.
But today we're exploring what happens to carbon when you push it to the absolute limits of physical reality.
The very edge of what's possible, yeah.
We are going on a journey to hunt for this theoretical superdense material known as BC8. It's often referred to as a superdiamond.
Which is a pretty wild concept on its own.
It really is. We're also going to unpack this 20-year-old mystery about exactly how normal diamonds melt under extreme pressure.
And, explore how these breakthroughs in material physics are paving the way to potentially triple the energy output of nuclear fusion.
Exactly. So I want you to imagine right now pressures that are 3 times greater than the very center of the Earth.
Just massive, unimaginable pressure.
Imagine temperatures hotter than the surface of the sun. And all of this is concentrated into a fraction of a second, inside a capsule no larger than a peppercorn.
It's almost hard to wrap your head around because carbon forms so many different structural arrangements.
Right, the allotropes.
Exactly, allotropes. And that's based purely on how the atoms bond to one another under varying environmental conditions.
Just depending on the heat and pressure they're exposed to.
Yeah. But carbon's behavior under extreme pressure has baffled the scientific community for decades.
Because it just defies the standard models.
Right. It completely defies our standard models of material science.
Yeah.
And resolving these mysteries, it's not just some exercise in theoretical science.
No, it has huge real-world implications.
It's the critical linchpin for understanding the deep interiors of planets, in our solar system and beyond.
And even closer to home.
Way closer to home. Understanding exactly how carbon behaves when it's crushed and heated is fundamentally required to achieve limitless, clean energy.
Through inertial confinement fusion.
Exactly. We are essentially mapping the phase changes of the hardest material known to humanity. And we're doing it in intervals of a billionth of a second.
A billionth of a second. That is just, wow. So getting into the theoretical predictions, they suggest that if you squeeze carbon hard enough, it'll eventually rearrange itself into that post-diamond structure we mentioned, BC8.
Right, the BC8 basis.
And this material is predicted to be super dense, like even tougher than a normal diamond and highly thermally conductive.
Which would make it the ultimate material.
Yeah, the technological dream here is that if BC8 turns out to be metastable, meaning once you create it under those crazy pressures, it doesn't just immediately revert back into normal diamond or graphite when you bring it down to room temperature.
Right, if it stays in that BC8 form.
Yeah, it could be this revolutionary new material. You could theoretically have a piece of BC8 that you just carry around in your pocket.
Effectively giving us the strongest material ever forged.
But looking closely at the actual mechanics of this atomic transformation, there is a pretty massive fundamental physical contradiction.
Yeah, there's a big hurdle.
Like, think of the carbon bonds in a normal diamond, like an incredibly intricate, virtually indestructible Lego structure.
The atoms are locked into this three-dimensional pyramid shape.
Right, making it the most rigid, robust configuration found in nature. So how on earth do you force these atoms to break those bonds and rearrange themselves into an even denser structure when they're already so tightly bound? It seems physically impossible.
Well, taking that indestructible Lego block and trying to just crush it into a tighter configuration requires an unimaginable amount of force.
Yeah, did that.
And earlier experiments proved just how stubborn that specific atomic structure actually is.
Yeah, there's that Discovery Science campaign at the National Ignition Facility, right?
Exactly. They aim to crush carbon to 20 megabars.
Which is an insane number.
To put that in perspective, 20 megabars is more than 5 times the immense pressure at the Earth's core.
5 times the core of the Earth.
Yeah, and the experiment failed to produce BC8.
Wait, really? It just failed?
It failed. The solid carbon simply retained its normal diamond structure far beyond the theoretical limits of its stability.
So why didn't it change?
The reason for this failure is just this massive energy barrier preventing the atoms from rearranging.
Oh, so just hitting it with brute force pressure wasn't enough?
No, the atoms were basically trapped in their existing lattice.
That Lego structure was just too strong.
Exactly. So the researchers had to devise an entirely new strategy, Instead of just violently crushing the carbon, they're using a sophisticated approach involving 35 terawatts of power and 156 kilojoules of ultraviolet energy.
35 terawatts. I feel like we need context for that number.
For context, 35 terawatts is roughly equivalent to the total power consumption of the entire planet.
Entire planet.
Yeah, the whole planet, concentrated into a tiny speck for a fraction of a second.
That is mind-boggling.
And the goal there is to simultaneously compress the diamond while also heating it to very high temperatures, bringing it right up near its melting line.
Ah, so you're not just squeezing it, you're getting it really hot.
Right. By tailoring this high-temperature compression pathway over an extended time frame, they give the atoms both the thermal energy and the physical time they need.
To actually overcome that massive energy barrier.
Exactly, theoretically coaxing them out of their rigid Lego-like grid and into that super-dense BC8 structure.
Okay, so since forming BC8 requires this highly specific, extended compression time to coax the atoms to shift, this naturally opens up a totally different avenue of inquiry.
Which is?
Well, what happens if you intentionally deny the diamond that extended time?
Ah, yeah.
Like, what if you just hit it with a sudden, single, violent shockwave?
That's the big question.
And this brings us to a massive breakthrough from the University of Rochester's Omega Laser facility. They recently resolved a mystery that had been frustrating scientists for 20 years.
Oh, the melting point discrepancy.
Yes. The theoretical predictions of a diamond's melting point were consistently off from the actual experimental data by a staggering 1,500 Kelvin.
Which is a huge margin of error in physics.
It's massive. To put that level of scientific frustration into perspective, imagine trying to bake a very delicate cake, but your oven thermometer is inexplicably off by thousands of degrees.
That sounds like a nightmare.
Right. Every time you try to bake it, the results make absolutely no sense compared to the recipe you're following.
Yeah, the entire scientific community was stuck with this massive discrepancy between their computer simulations and physical reality.
Completely unable to map the melting point of the most important carbon allotrope.
And trying to bake that delicate cake when you have no idea what the oven is actually doing, it perfectly illustrates the diagnostic nightmare scientists were facing.
Because it's hard to even see what's happening.
Right. Capturing the atomic structure of a melting diamond in real time is monstrously difficult.
Why is that?
Well, carbon is a very light atom, meaning it scatters very few X-rays, making the diagnostic signal incredibly faint.
So it's physically hard to photograph or image.
Exactly. But at the Omega Laser facility, researchers managed to capture X-ray diffraction data in a billionth of a second.
A billionth of a second.
Yeah, at 1 terapascal of pressure.
Wow.
With these enhanced diagnostics, they finally captured the exact moment of transition.
And what did they find?
They proved that when subjected to a single rapid shock wave, the diamond remains completely trapped in its normal cubic structure all the way up until the moment it completely melts.
Wait, so it never briefly transitions into BC8?
No, or any other intermediate phase first. Because a single shock simply does not afford the atoms the time needed to cross that massive energy barrier.
That makes sense.
And this discovery leads to a truly remarkable physical realization.
What's that?
Diamond actually becomes denser when it melts.
Denser when it melts.
Yeah. The high-pressure liquid metallic carbon is denser than the solid diamond itself.
That is so weird.
It means a chunk of solid diamond would float in a pool of liquid metallic carbon.
Oh, behaving exactly the way ice cubes float in a glass of liquid water.
Exactly like that.
Okay, so applying this realization shifts the focus toward inertial confinement fusion, or ICF.
Right, back to the National Ignition Facility.
Yeah, they use tiny millimeter-scale capsules made of high-density carbon, which is essentially synthetic diamond.
Yep.
And inside this tiny diamond shell is a frozen layer of deuterium and tritium fuel. Lasers hit the target, generating this intense X-ray bath that ablates or forcefully blows off the outer layer of the diamond.
And according to Newton's third law, that outward explosion pushes the rest of the capsule inward.
Right, at hundreds of kilometers per second.
Compressing the fuel until it reaches temperatures and pressures capable of sustaining a nuclear fusion reaction.
But looking closely at the mechanics of this implosion process reveals a really delicate balancing act.
Very delicate.
Think about pushing a child on a swing. If you want them to go high and stay balanced, a smooth, controlled, continuous push is infinitely better than a sudden, violent shove.
Because a violent shove would just cause the swing to jerk erratically.
Exactly, and potentially tip over.
Yeah.
A smooth, controlled implosion seems mechanically superior to a violent shock when trying to compress this volatile fusion fuel into a miniature star.
Yeah, if you violently shove that swing, the chains jerk wildly and the entire system loses stability.
Which is bad news for fusion.
Very bad. In fluid dynamics, we call that erratic jerking a hydrodynamic instability.
Okay.
For the fusion implosion to work, the diamond capsule must melt into a perfectly uniform liquid shell.
And if it doesn't?
If it does not melt completely, solid chunks of diamond remain. Those solid imperfections cause uneven pressure distribution.
Like pushing the swing weirdly?
Right, and during an implosion, any tiny imperfection grows exponentially, basically tearing the capsule apart.
Oh, wow. So how did they fix that before?
Previously, to guarantee that the diamond melted completely and avoided these imperfections, the National Ignition Facility used a massive, violent initial shock of 1.2 terapascals.
Oh, just a brute force sledgehammer method?
Exactly, a sledgehammer to ensure the capsule liquefied. But the new melting data from the Omega Laser Facility proves that the diamond can actually melt completely at lower pressures than previously thought.
So they don't need the sledgehammer anymore?
No, scientists can use a slower, weaker initial shock to still achieve a fully liquid capsule.
And why is that better?
This lower entropy path is absolutely vital because it prevents the fuel from heating up too early in the process.
Oh, okay.
When the fuel remains cooler during the initial compression phase, it is much more compressible later on.
Got it.
Theoretical models suggest that by making the fuel more compressible through this gentler initial shock, we could potentially triple the maximum energy yield of the fusion reaction.
Triple it. Using the exact same amount of laser energy.
Using the exact same amount of laser energy.
That is incredible. So putting this into practical application involves the SQN design and this diagnostic tool called streaked refraction enhanced radiography.
Or RER for short.
Right, RER. And it operates almost like an ultra-fast, ultra-precise X-ray video camera.
Yeah, scientists use a zinc foil backlighter driven by 22 laser beams to create a brilliant X-ray point source,
allowing them to image the density gradients inside the capsule as it implodes.
They track the boundary between the melting diamond ablator and the incredibly cold deuterium-tritium ice fuel.
And through this RER imaging, they directly measure the acceleration of that specific fuel ablator interface.
Right, and they measured a highly controlled, gentle acceleration of exactly 20 plus or minus 1.8 micrometers per nanosecond squared.
That is so precise.
By tailoring the laser pulse to provide this gentle acceleration right after the first shock, they are physically stabilizing the capsule as it crushes inward.
Just keeping that swing perfectly balanced.
Exactly. The precision of hitting exactly 20 micrometers per nanosecond squared is the key to preventing the system from tearing itself apart.
What happens if they miss that number?
Well, when a shock wave passes through an uneven fluid interface, it triggers what is known as the Rickmeyer-Meshkov instability.
Which is?
Imagine a massive shock wave hitting a puddle of water. It causes violent, jagged splashing.
Oh, I see.
Later in the implosion, as the lighter carbon ablator pushes against the heavier compressed fuel, you get Rayleigh-Taylor instabilities.
So it's just instability after instability.
Yeah, but by introducing that specific gentle acceleration, the physical mechanics of the implosion change dramatically.
How so?
The initial jagged splashing of the Rickmeyer-Meshkov growth is replaced by stable Rayleigh-Taylor oscillations.
So instead of the flaws tearing the capsule apart.
The boundary layer naturally oscillates and self-corrects to a degree.
That is fascinating.
The ultimate physical goal is preventing the carbon ablator material from mixing into the central hotspot of the fuel.
Right, because if carbon mixes into the deuterium-tritium fuel,
it radiates energy away, cooling the hotspot and killing the fusion reaction before it can truly ignite.
which ruins the whole thing.
Exactly. The precise mapping of the diamond melting curve is the exact mechanism that allows us to fine-tune that acceleration perfectly.
Man. Okay, zooming out from the microscopic scale of a millimeter-sized fusion capsule to the scale of entire planets provides a staggering perspective on these material physics breakthroughs.
It really does connect the micro to the macro.
Like crushing tiny synthetic diamonds in a laboratory translates directly to understanding the cosmos.
Specifically, the ice giants in our own solar system.
Yeah, we take laser facilities that fit inside a few football fields and use them to replicate extreme environments that exist millions of miles away in deep space.
It's wild to think about.
These fraction-of-a-second laser pulses eliminate the physical processes happening inside the swirling, crushing depths of massive planetary bodies like Uranus and Neptune.
And, the pressures reached in these microscopic laboratory experiments actually exceed the extreme pressures found deep inside the mantles of Uranus and Neptune.
They exceed them.
Yeah. Astrophysicists have hypothesized this phenomenon known as diamond rain for years.
Diamond rain. Just the name sounds like sci-fi.
It does. The theory suggests that the immense heat and pressure inside these ice giants cause hydrocarbons, like methane, to physically break apart.
Okay, so the molecules split?
Right. And then the carbon atoms bond together, crystallize into diamonds, and physically sink through the fluid interiors of the planets toward the core,
Just raining diamonds down into the core.
generating massive amounts of heat and driving planetary magnetic fields as they fall.
That is unbelievable.
Until now, this was largely based on theoretical modeling.
But now we have the data.
Exactly. The recent experiments provide the first empirical, experimental benchmarks for these models.
Wow.
We have concrete data on how carbon behaves, melts, and crystallizes at those exact planetary conditions.
Which brings all these different fields of science together.
Yes. This synthesis of astrophysics, material strength, geophysics, and high-energy density physics is largely driven by collaborative communities.
Like the American Physical Society's topical group on compression of condensed matter.
Yeah, which recently broadened its scope to include static high compression. They are bringing together disparate fields to build a unified understanding of matter under extreme conditions.
It's just so incredible what they're achieving.
It really is. And I'd say mastering the ability to precisely map and manipulate the phase changes of the hardest materials on Earth, predicting their structural shifts down to a billionth of a second and a fraction of a terapascal, presents a completely new paradigm.
Oh, absolutely.
The implications stretch far beyond fusion or planetary science.
What do you mean?
Well, the next era of advanced manufacturing won't just be about finding new materials that naturally occur in our environment.
Right.
It will be about using perfectly timed laser shock waves to artificially forge entirely new states of matter materials with thermal, structural, and electrical properties that simply do not naturally exist anywhere in our universe.
Subscribe to the podcast series Nuclear Locomotive, Neural Sawdust, and Synthetic. Namaste, thank you, and Akui. Good luck.